In 1815, Mount Tambora erupted, sending a grisly veil of ash around the globe and killing tens of thousands. The climate cooled, crops failed, the world felt a shock. But supervolcanoes like ancient Mount Toba are far larger, tens of times the debris and power. An eruption at that scale today could be catastrophic, potentially claiming up to 1 billion lives. Around 20 supervolcanoes are active and sleeping beneath Earth's crust. Their threat extends beyond local damage. Global climate and agriculture could be disrupted for decades. Rather than wait for disaster, engineers ask, can we manage these sleeping giants? Understanding the chamber geometry is the first step, where heat, pressure, and fluids meet. Any intervention must be precise, measured, and safe. Next, one bold proposal to do both: remove danger and make power from it. We begin with engineering at depth. One NASA engineer proposes a radical idea: tap the magma's heat with deep boreholes. Drill several kilometers deep in a ring around the chamber, keeping distance to avoid triggering it. Cold water injected into hot rock becomes superheated and returns as steam to drive turbines. The location of each borehole is critical. Too close, and you risk an unintended eruption. Careful modeling and monitoring would be required to manage stress and fluid flow. If done right, the system provides continuous renewable power while gradually cooling the magma. This is not instant. Over tens of thousands of years, heat extraction could neutralize a chamber. But mantle plumes are continual. New supervolcano seeds can form on geological timescales. To protect civilization, we would need long-term monitoring and many such projects worldwide. The ethics are complex. Risk, benefit, who decides, who pays, all must be addressed before drilling. Still, turning a planetary hazard into a renewable resource reframes risk as opportunity. In 1991, Mount Pinatubo injected tens of millions of tons of sulfur into the stratosphere and cooled the planet. Aerosols reflect sunlight, like sunscreen for Earth, temporarily lowering global temperatures. A small mass of sulfur aloft can offset the warming of many tons of carbon dioxide for a year. But the effects may be uneven. Weather shifts could harm crops and livelihoods in some regions. Control of climate interventions could become geopolitical, raising conflict risks. Any deployment would need global governance and robust research on side effects. MIT and others have proposed a space-based shield, millions of reflective elements at the Sun-Earth balance point. To reduce sunlight by about 1.8%, the shield would be enormous, country-sized, but reversible. Alternately, space mirrors could be targeted to warm or cool specific regions as needed. All these tools can buy time to decarbonize, but none remove the need to cut emissions. They are gap fillers, not substitutes for long-term planetary stewardship. Next, working with life itself to manage climate and ecosystems. Large-scale ecosystem work, like the Great Green Wall, sequesters carbon, restores soils, and creates livelihoods. A belt of trees across Africa could remove hundreds of millions of tons of carbon and stabilize landscapes. Bioengineering can amplify nature. Plants grown 40% larger, algae producing fuel, microbes generating electricity from waste. These approaches turn biology into factories, clean fuels, power, and carbon sinks. De-extinction ideas, like cold-adapted elephant hybrids, could help stabilize permafrost and preserve carbon stores. Mechanical trees capture CO2 on plates and can sequester as much carbon as thousands of living trees each. Deployed at scale, they could offset massive emissions where forests cannot grow. But they require energy, materials, and careful life cycle accounting. Working with local communities and ecosystems will determine success or failure. Biology gives us scalable tools, cells as machines, to steward life on Earth. Excess CO2 acidifies oceans and weakens food chains. Some propose restoring chemistry with rock weathering. Pulverized basalt can absorb CO2, but the scale is massive and the methods extreme. An extreme concept even invokes subterranean blasts. Technically possible, but ethically perilous. Safer interventions include artificial reefs from sunken structures that revive fisheries and sequester carbon. Reefs can multiply biomass and boost ocean resilience, protecting coasts from storms. Thwaites Glacier in Antarctica is a critical tipping point. Warm currents are undermining it from below. A bold plan, a 100-kilometer underwater curtain to block warm water and stabilize the ice. In the Arctic, wind-driven pumps and floating umbrellas could seed winter ice where it is melting fastest. All these projects demand vast resources. Each carries ecological, social, and governance trade-offs. Yet protecting oceans and ice could prevent catastrophic sea level rise, safeguarding millions of lives. Human energy use has exploded, thousands of % growth, and if unchecked, will thermally overwhelm Earth. Even clean energy on planet creates waste heat. At extreme scale, it could raise global temperatures by tens of degrees. Deserts hold vast solar potential. Covering small percentages of Earth could power civilization. But huge arrays can alter land albedo and weather. Terrestrial solutions have trade-offs. Space-based solar collects uninterrupted sunlight and can radiate waste heat to space, avoiding Earth heating. Proposals already exist. Kilometer-scale orbital arrays designed to deliver gigawatts to Earth. The safer long-term path: relocate power-hungry manufacturing to space where heat is dumped to the void. A space elevator could reduce launch costs dramatically if we can create tether materials strong enough. Beyond the elevator, orbital rings could become planetary infrastructure, transport energy and habitats. But space debris poses existential operational risks. AI-guided lasers and capture systems would be essential. To avoid stripping Earth, raw materials could come from asteroids, reducing terrestrial impacts. This supply chain enables megastructures without catastrophic extraction at home. Imagine energy and heavy industry in space, Earth as a preserved sanctuary, and planetary systems managed responsibly. Combining engineering, biology, and governance could secure a safe future for life. The question remains: will we build the tools to steward our home or let shocks define us?